This week's experiment is called Enthalpy of Neutralization. The outline of this pre-lab lecture will include some definitions and concepts, some graphs that you need to know how to plot, the neutralization reactions that you will be conducting in the experiment, and then calculations, temperature difference, determining the calorimeter constant, which would include heat lost by hot water, heat gained by cold water, and finally using these two bits of information to calculate the calorimeter constant. Determining the molar enthalpy of neutralization will include temperature difference, heat absorbed by reaction mixture, heat absorbed by the calorimeter, total heat absorbed, molarity, and then all these information going to calculate the molar enthalpy of neutralization. And then finally what you need to know about the experiment. So some definitions and concepts. When things react, the energy change associated with the reaction frequently involves the transfer of heat. Thermochemistry is the study of heat changes and transfers associated with chemical reactions. A calorimeter is a well-insulated container that is used to measure the heat released or absorbed by a physical or chemical process that takes place within it. The chemical system is the part of interest, usually includes the reactants and products of the reaction. The surroundings is everything else in the immediate vicinity of the system. The universe is the system plus the surroundings. So here is a little picture connecting the chemical system, the surroundings, and the universe. The final state is the condition that exists when we stop taking measurements on a system. The initial state is the condition that exists when we start taking measurements on a system. The temperature change, or delta T, is the difference between the final temperature of the system and the initial temperature of the system. In mathematical terms, delta T equals T final minus T initial. The internal energy, E, is the sum of the potential and kinetic energies for each particle in a system. The change in internal energy, delta E, is the change in internal energy of the final state of the system and the internal energy of the initial state of the system. In mathematical terms, delta E equals E final minus E initial. The difference between the internal energy of the products and that of the reactants at constant volume is delta E equals E products, or the internal energy of the products, minus E of the reactants, or the internal energy of the reactants. To measure the internal energy, we must measure both heat and work, or PV work, pressure volume work. We must consider the work done by the change in pressure and the work done by the change in volume separately. To eliminate the need to consider PV work separately, the variable of enthalpy, H, is used. And enthalpy is defined as the internal energy plus the product of the pressure and volume, or H equals E plus PV. If at constant pressure, the change in enthalpy is defined as the change in internal energy plus the product of the constant pressure and the change in volume, delta H equals delta E plus P delta V. The change in enthalpy is also defined as the difference between the enthalpy of the products and that of the reactants at constant pressure. Delta H is equal to H of the products, the enthalpy of the products, minus H of the reactants. or enthalpy of the reactants. When a chemical process or reaction occurs, the enthalpy of the system either increases or decreases. An exothermic reaction releases heat and results in a decrease in the enthalpy of the system. Let me say that again. An exothermic reaction releases heat and results in a decrease in the enthalpy of the system. On the other hand, an endothermic reaction absorbs heat and results in an increase in the enthalpy of the system. Let me repeat that again. An endothermic reaction absorbs heat and results in an increase in the enthalpy of the system. The calorimeter constant, or C-cal, is the amount of heat that the calorimeter absorbed per degree rise in temperature, or the heat capacity of the calorimeter. So, two graphs will be generated in this experiment. A temperature time plot for hot and cold water, and a temperature time plot for a neutralization reaction. So what do these plots look like? Okay, for temperature time plot for hot and cold water mixing, you get a graph similar to this, where hot water is represented by the red diamonds, the temperature versus time for the cold water is purple squares, and the temperature of the mixture is blue triangles. What you need to do next, once you get this raw data and plot it, you need to assign time of mixing, and this is the exact time where you combined the hot and cold water. Next, draw a trend line or a straight line through the hot water to the time of mixing, and where this line intersects the time of mixing, this is T hot initial. And you'll do the same for the cold water, and where this line intersects the time of mixing line, that's T cold initial. Now T final is where a straight line through the mixing temperatures intersect time of mixing, as shown here on this plot. So delta T cold is T final minus T cold initial, and delta T hot is just T final minus T hot initial. So the temperature plot for a neutralization reaction will look similar to this, where the temperature versus time data for the base is the red diamonds. For the acid, it will be the green squares, and the temperature data for the mixture is blue triangles. Now, as you can see, the acid temperature and the base temperature will not be the same. So once again, you have to establish time of mixing, and this is the exact time where you mix the acid and base together. You will draw a line through the data for the base, and you'll get T base initial, where this line intersects time of mixing. And you'll do similar with the acid, and where this line intersects the time of mixing line, that's T acid initial. T final is where the line drawn through the mixture data intersects the time of mixing line, or that's T final. Now, T initial is equal to T acid initial plus T base initial divided by 2. And then T final, or delta T, is equal to T final minus T initial. So the neutralization reactions that will be performed in this experiment will be, you're going to take some sodium hydroxide plus hydrochloric acid, and that will yield sodium chloride plus water. You're also going to take sodium hydroxide plus sulfuric acid and get sodium hydrogen sulfate plus water. You're also going to do sodium hydroxide plus phosphoric acid to get sodium dihydrogen phosphate plus water. And as you can see, all three neutralization reactions yields a salt plus water. So let's do some calculations. Temperature difference, delta T. During a calorimetry experiment using hot and cold water, a student measured the initial temperature of the hot water as 37.5 degrees C and the initial temperature of the cold water as 22.4 degrees C. After mixing the hot water with the cold water, the student measured the temperature of the mixture as 27.6 degrees C. What are the delta T's for the cold water and the hot water? Well, delta T is equal to T final minus T initial. So delta T cold initial is 22.4 degrees C. Delta T hot initial is 37.5 degrees C. T final is 27.6 degrees C. So delta T cold is 27.6 degrees C minus 22.4 degrees C, or T final minus T cold initial. And that is equal to 5.2 degrees C. Significant figures. You're subtracting, so it goes by least number of decimal places. Each of the temperatures have one decimal place, so your answer should have one decimal place. So delta T hot is equal to 27.6 degrees C minus 37.5 degrees C. T final minus T hot initial. And that is equal to negative 9.9 degrees C. And that negative sign is important. Keep the negative sign with the value. And here's your additional practice example. Determining the calorimeter constant. You'd first need to determine the heat lost by hot water. And the formula to use is Q hot equals V hot in milliliters times D of H2O in grams per milliliter times delta T hot in degrees C times S of H2O in joules per gram per Kelvin. Now, what do these variables mean? V hot is the volume of hot water used. D, H2O is the density of hot water, or 1.0 grams per milliliter. Delta T hot is the temperature difference for the hot water. And SH2O is the specific heat for water, and that is the amount of heat required to raise the temperature of 1 gram of water 1 degree Celsius. And for water, this constant is 4.184 joules per gram per Kelvin. And as you can see from the formula, we have a degree C, but we also have a Kelvin. And we don't have to worry about this because delta T in degree C is equal to delta T in Kelvin. We don't have to convert temperatures when working with delta T's. Only when working with delta T's. Now, the heat gained by the cold water is another variable you need to calculate for determining the calorimeter constant, and that is Q cold equals V cold in milliliters times DH2O in grams per milliliter times delta T cold in degrees C times S of H2O in joules per gram per Kelvin. And once again, V cold is the volume of cold water used. DH2O is the density of the cold water, which is still 1.0 grams per milliliter. Delta T cold is the temperature difference for the cold water, and the specific heat of H2O, SH2O, is still 4.184 joules per gram per K. Now, the heat absorbed by the calorimeter is another factor you need to calculate. And to do this, you have to remember that all the heats in a system needs to add up to 0. 0 is equal to Q hot plus Q cold plus Q cal. And so rearranging this to get Q cal, or the heat of the calorimeter, heat absorbed by the calorimeter, is equal to negative heat of the hot water minus Q of the cold water. And then finally, all this gets to the calorimeter constant, or C cal is equal to Q cal divided by delta T of the cold water. So let's do an example. During an experiment, a student placed 25.00 milliliters of cold water into a calorimeter and measured its temperature as 27.45 degrees C. His lab partner measured out 25.00 milliliters of hot water and measured its temperature as 38.22 degrees C. They poured the hot water into the cold water and waited for a while to allow the system to equilibrate. They then measured the final temperature as 28.33 degrees C. Using this data, calculate the calorimeter constant. So step 1, we need to determine delta T cold and delta T hot. And remembering, delta T cold is equal to T final minus T cold initial, or 28.33 degrees C minus 27.45 degrees C. And that is equal to 0.88 degrees C. And delta T hot is equal to T final minus T hot initial, or 28.33 degrees C minus 38.22 degrees C, or negative 9.89 degrees C. And remember, please keep that negative sign there. Step 2 is determining heat loss by hot water, Q hot. And remember, Q hot is equal to V hot times density of water times delta T hot times the specific heat of water. So Q hot is equal to 25.00 milliliters times 1.0 grams per milliliter times negative 9.89 degrees C times 4.184 joules per gram per Kelvin, and that is equal to negative 1.0 times 10 to the third joules. Now, for significant figures, we're multiplying, so we have to go by least number of significant figures. Our density term has only 2 significant figures, which is our least number of significant figures, so our answer has to have 2 significant figures. Step 3 is determining the heat gained by the cold water, or Q cold. And Q cold is V cold times the density of water times delta T cold times the specific heat of water. So Q cold is equal to 25.00 milliliters times 1.0 grams per milliliter times 0.88 degrees C times 4.184 joules per gram per K. And that is equal to 92 joules. Step 4 is determining the heat gained by the calorimeter, or Q cal. Q cal is equal to negative Q hot minus Q cold, or negative times negative 1.0 times 10 to the 3 joules minus 92 joules, or 908 joules. Now, to determine the significant figures, we're subtracting, so we have to go by least number of decimal places. So we have to change the 1.0 times 10 to the 3 into the same type of number as 92, or change 92 into an exponent of 10 times 10 to the third. It's just easier to put 1,000 minus 92 to get 908 joules. And step 5, determining the calorimeter constant, C cal. C cal is equal to Q cal divided by delta T cold. So 908 joules divided by 0.88 Kelvin. And remember, degree C is equal to delta T, and degree C is equal to delta T and K, so I just put the K there. And that is equal to 1.0 times 10 to the third joules per Kelvin. And this is what you'll be doing in the first part of the experiment, is determining the calorimeter constant. And here's your additional practice example. . determining the molar enthalpy of neutralization. And we're just going to do an example to work through all this. During a neutralization reaction between 5.00 milliliters of 0.9978 molar sulfuric acid and 5.00 milliliters of 1.005 molar sodium hydroxide, which yielded a mixture of sodium sulfate and water, a student measured the initial temperature of the acid, or sulfuric acid, as 28.73 degrees C, and the initial temperature of the base, sodium hydroxide, as 27.67 degrees C. After mixing the acid and base together and the reaction is complete, the student measured the final temperature as 29.49 degrees C. What is the molar enthalpy of neutralization for this reaction? And you just determined the calorimeter constant as 1.0 times 10 to the third joules per Kelvin. All right, step one is to write out the balanced neutralization reaction. So you take the acid and add it to the base. So sulfuric acid plus sodium hydroxide will yield sodium sulfate plus water. Now to balance it, you'll need 2 sodium hydroxides and you'll need 2 waters. Step 2 is determining delta T. Delta T is equal to T final minus T initial. And remembering, T initial is equal to T acid initial plus T base initial divided by 2. So T initial of acid is equal to 28.73 degrees C. T base initial is equal to 27.67 degrees C. And T final is equal to 26.91 degrees C. So T initial is equal to 28.73 degrees C plus 27.67 degrees C divided by 2 to get 28.20 degrees C. And so delta T is equal to 29.49 degrees C, T final, minus 28.20 degrees C, T initial, to get a delta T of 1.29 degrees C. The next step is determining the heat absorbed by the reaction mixture. And Q absorbed is equal to V of the mixture in milliliters times D mix of the mixture grams per milliliter times delta T in degrees C times S of the mixture in joules per gram per K. Now V mix is the total volume of the mixture. V base plus V acid, the volume of the base plus the volume of the acid. Density of the mixture is the density of the salt produced during the reaction. So it's the density of the salt, or in this case, sodium sulfate. S mix is the specific heat of the salt produced during the reaction, or in this specific example, the sodium sulfate. Now, how do I get the density and the heat capacity of my salt? Well, you have this lovely reference table in your lab manual, and it gives you the salt, sodium chloride, sodium hydrogen sulfate, sodium sulfate, sodium hydrogen phosphate, sodium dihydrogen phosphate, and sodium phosphate. It also gives you concentrations, and we can assume that the concentration of the salt produced by any of the neutralization reactions will be 1.00. Gives you the heat capacity and the density. And to use this table, you find your salt, and you look over, and it will give you the heat capacity and the density. So sodium sulfate is our salt, so our heat capacity is 3.76 joules per gram per K, and our density is 1.12 grams per milliliter. So Q absorbed is equal to 10.00 milliliters, or the volume of the acid plus the volume of the base. So 5.00 plus 5.00 equals 10.00 milliliters times the density of the salt. From the table, it's 1.12 grams per milliliter, times our delta T, 1.29 degrees C, times S. From the table, 3.76 joules per gram per K, and we calculate that as 54.3 joules. Step 4 is determining the heat absorbed by the calorimeter. Q cal is equal to C cal, or the calorimeter constant, times the delta T. So Qcal is 1.0 times 10 to the third joules per K, or Ccal, the calorimeter constant, times delta T of 1.29 degrees C. And you get Qcal equals 1.3 times 10 to the third joules. Step 5 is determining the total heat absorbed. So Q total absorbed is equal to Q absorbed plus Qcal, or in our case, 54.3 joules plus 1.3 times 10 to the third joules, which is equal to 1.4 times 10 to the third joules. Step 6 is to determine the number of moles of acid. And to do that, we have to use the molarity of our acid. And we know that molarity is equal to moles per liter. So moles of acid is equal to the molarity of the acid times the volume of the acid in liters. So moles is equal to 0.9978 moles per liter times 5.00 milliliters, and we need to convert it to liters, and there's 1,000 milliliters in 1 liter. And we get 4.99 times 10 to the minus 3 moles of acid. And then step 7, determining the molar enthalpy of neutralization. And delta H neutralization is equal to the total heat absorbed divided by the moles of acid. And Q total released is just equal to the negative Q of the total absorbed. So the heat totally released is equal to the heat totally absorbed, the negative of the total absorbed. So Q totally released is negative 1.4 times 10 to the 3 joules. And so delta H neutralization is equal to negative 1.4 times 10 to the third joules divided by 4.99 times 10 to the minus 3 moles. And that is equal to negative 2.8 times 10 to the 5th joules per mole. Now, when things are released, your value for thermochemistry should be negative. If it's absorbed, it needs to be positive. And that's why we have a negative for delta H of neutralization, because it relies on something being released. So here's your additional practice example. So things to keep in mind for the experiment. Read the white procedure pages and complete the pre-lab assignment. Make sure you hand in your graph that you used for problem number 3. You do get points for that graph. Show all work when doing calculations. Make sure all your answers have the proper units and significant figures. In this experiment, you will be either using a computer or a PDA device to plot your data. Your TA will hand you the instructions on how to properly use the devices, and this handout will be your modifications to the experiment. So it will tell you how to do the experiment using the computer or the PDA. If you're using a PDA, you will need your student ID card to check out the PDA. So you will not know if you will be using a PDA, so please bring your student ID card with you to lab this week. Make sure you pay attention to the chemical alert and caution boxes in the white procedure pages. You will be dealing with acids and bases, so please know how to handle them properly and the safety precautions associated with each of them. You will be measuring 2 different acid-base neutralization reactions during this experiment. However, datasheet 4 does not provide enough room for all the data. So you will need to draw a line in the middle of the column that says first and in the middle of the column that says second. Label the first column HCl and label the second column other acid. And your TA will assign you the other acid. It will either be sulfuric acid or phosphoric acid. Record the correct number of significant figures for all your measurements. Put units on all your measurements. Show all work when doing calculations. All answers to calculations should have the correct number of significant figures. So here is the answers to the additional problems. And as always, if you have any questions, please go see your TA before coming to class. Do not go into lab and have questions. That will be too late. Go to him or her before your lab.